Now, today we're going to finish undergraduate dynamics conventionally defined in this topic, which is the three-dimensional equations of motion. And after that, I will start the bridge topic, which connects the undergraduate dynamics to structural dynamics. And this is what we call free vibration of single degree of freedom system. Of course, before that, I will show you the difference between the undergraduate dynamics and the graduate dynamics. And this may be a little bit teasing the class, because even I show you what will be covered in graduate level structural dynamics, you will still not be able to learn the material until maybe 2 or 3 years later. But at the time, if you decide to take structural dynamics, the first thing you should do is to come back to your notes on this one. This is going to be the topic to help you to remind yourself, where does structural dynamics begin? And this is the topic to connect these two, which I, over the past few years in my teaching career, I believe that this is useful for many students, because I'm teaching structural dynamics right now, and many graduate students told me that they have no idea what they learned in dynamics, just like fresh, and that, of course, makes sense. All right, so let's continue our discussion on three-dimensional equations of motion, and this will be example 35. And the governing equation for the force equilibrium and the moment equilibrium, the most general form, you already have it, right? You remember that for the force equilibrium in 3 different directions, because we always have to take the force equilibrium at the component level. In the 3-dimensional world, you always have 3 expressions for the force equilibrium. The same thing with moment equilibrium. Now, for the moment equilibrium, the biggest difference is the contribution of the angular motions in other directions, affecting the angular information, or in this case, the angular velocity or angular acceleration in the direction under consideration. So today we're going to use that exercise, that moment equilibrium, in this example 35. What is example 35? Let's consider this part here, which, did I start the problem? I think I started the problem, right? And
yes.
Where are we at? We finished the problem definition, right?
Yeah.
No, there's a point A, there's point B, and let's define this thing. Of course, I used it.
Yeah, you got to the point where it says, what will the reactions at point A and B?
Correct. So we are looking at
there you left off.
And B is supported by the hinge, which means that B is allowed to spin, to move, to rotate, but B cannot move vertically. And this point A is actually sitting in air. Why is it sitting in air? Because this bar is in motion, is in angular motion. Now, this is also another major difference between statics and dynamics, because in statics, you cannot consider this kind of structure, right? How can you consider that the beam is just supported by one end and the other end will what? Will sag, correct? But in dynamics, take a rope as example. If you try to spin the rope, the free end of the rope actually was not supported, correct? Therefore, this is one example of what we call dynamic equilibrium. Another case to show you, in statics, this is not possible. But in dynamics, yes, it is possible. So we are looking for the reactions at B, and if we use the XYZ, I know I say that it's the vertical axis, but if you keep the definition for coordinate systems consistent, we're going to say this is going to be the XYZ, like this. Same thing for point A and point B. Then what we are looking for is essentially reaction forces at A and B. And if we define those by following the positive direction, so this is going to be RAX. I know it may look a little bit messy, but just to make sure that we don't leave any force out of our consideration. So at point A, you have 3 possible forces. At point B, you have 3 possible reactions, right? So let's define them and consider them so we won't forget. Just be careful that the symbols may come a little bit messy here. RBX. So we have 3 here and 3 here. Now, what information we are provided? We know the total length of this rod or this bar is 1 meter. We know this whole thing is 1 meter. With constant mass density, the center of gravity is at mid-span, which is at the center of geometry. We also know that this angular velocity omega here is 10 radius per second. And we also know the mass of the bar is 5 kilograms. The mass of the bar is 5 kg. Now, what we need to do is find R A, I'm going to say is a vector, so I consider 3 of them, and RB. How is that? This way you know that for RA and RB, it's not just one quantity. If I say it's a vector, you consider 3 components. This will save us our time, so we don't have to copy it. Now, before I finish dynamics, you will notice the way I teach, and this is also the way I train all students in my class. You must, before you start the problem, the very first thing I always do is what? Is define the problem, which is this. This is, in fact, probably the most important thing. You always be provided with all different kind of conditions, but if you don't know what you're after, how do you know you are going toward the right direction? The first question you need to ask yourself to become a good engineer is, what am I after? What information I'm looking for? This, before you solve any problem, you must learn to write this down, to tell yourself that this is what I'm looking for. Otherwise, given this kind of problem, I could ask you lots of different things. So if you don't know what you're after, and you're not going to be taking the right step toward this, and then you will be not really using your time most wisely. So how do we solve the problem? Well, first of all, let's determine the mass moment of inertia and the products of inertia if we need it. Now, for this bar, the reason why we call this a bar is because the dimension on the YZ direction, which is the diameter or the radius of the bar, is relatively small. And that being said, the difference between small rod and also a cylinder. So what's the difference between these two? If you think about it, you know that we talk about this, right? In mass moment of inertia, and later on we start considering something actually dimension in this direction becomes greater. Which means what? Which means that if you consider the center of gravity here, and you also define the x, y, z. What is the difference between the small rod versus a real cylinder? Now, we will not spend time to actually doing the math. I will just give the result. If you have the textbook, go to the back of the textbook. On this table, there are 2 different objects. One is the bar, and the other is a cylinder. Now, if you look at this, you will notice that for the mass moment of inertia in the y and z direction, there's no difference. So if we call this one x, this one y, this one z, x, y, z. The only difference is the mass moment of inertia with respect to the x-axis. That's the mass moment of inertia, which is what? Which is here, we call it Ixx. This is also Ixx. Before, when we consider the small bar, we said this Ixx is just 0. That's what we said, right? We never consider it because we said the dimension is so small. Why the dimension is so small? It's because Ixx equals to the integral of r squared dm over the entire volume. What is r squared? R squared is actually the radius in here, which means that when the radius is very small, what happens to the r squared? It becomes even smaller. Hence, we ignore Ixx.